Hello students, I am Shrikala, faculty from the Department of Mechanical Engineering, Global Academy of Technology. Today, in this presentation, I am going to summarize the vapor power cycles. A thermodynamic power cycle which continuously converts heat into work using vapor or steam as working fluid is called a vapor power cycle. The schematic of the vapor power cycle is shown in the figure. Any vapor power cycle consists of four important components: the boiler, turbine, condenser, and a pump. Heat is transferred to the boiler in order to increase the pressure and temperature of the water. This gets converted into the steam and gets expanded in the turbine, producing shaft work. The steam leaving the turbine condenses into water in the condenser, rejecting heat. Then the water will be pumped back to the boiler. Here, the change of phase occurs from liquid phase to vapor phase in the boiler and back to liquid phase in the condenser. Now, the efficiency is given as net work divided by heat supplied. Net work is the turbine work minus the pump work divided by the heat supplied is the heat is supplied in the boiler. Here in this slide, the schematic of a Carnot vapor power cycle and the TS diagram is shown. The Carnot cycle is the most efficient cycle operating between the two specified temperature limits. This Carnot cycle mainly consists of four processes. Two are isothermal processes and two isentropic processes, that is constant entropy. Process 1 to 2 is isentropic expansion of the steam in the turbine. That means steam entering the turbine as shown here is dry saturated steam. After the steam expands, it gets converted into wet steam doing some shaft work. The wet steam is then passed through the condenser and the steam gets condensed. And the condition of the steam coming out is at 3. So this is again a wet steam. Then it is pumped back to the boiler and the 4 point is saturated liquid. That means the condition of the steam which is entering the boiler is purely water. And in the boiler, 4 to 1 is isothermal heat addition or expansion is given. So heat is added in the boiler till the saturated liquid completely gets converted into dry saturated vapor. And 1 to 2 is the isentropic expansion of the steam in the turbine. 2 to 3 is isothermal compression of the steam in the condenser. 3 to 4 is isentropic compression, that is pumping work, and 4 to 1 is the constant temperature heat addition in the boiler. The net work is given by the turbine work minus pump work by heat supplied. And the work is specified in terms of enthalpies, where H1 is the enthalpy of the steam entering the turbine, H2 is the enthalpy of the steam leaving the turbine or entering the condenser, H3 is the enthalpy of the steam leaving the condenser or entering the pump, and H4 is the enthalpy of the steam leaving the pump or entering the boiler. So now the efficiency is given by turbine work minus pump work by heat supplied. So turbine work is H1 minus H2 and the pump work is H4 minus H3 and the heat supplied is H1 minus H4. So after simplification and converting into in terms of temperature, the efficiency is given by TL by TH. TL is nothing but the lower temperature, that is temperature in the condenser, and TH is the temperature in the boiler. In this slide, we are going to see the simple Rankine cycle. Again, simple Rankine cycle, we have the same four processes, but the process 1 to 2 and 3 to 4 are turbine, that is isentropic expansion, the turbine, and isentropic compression or the pumping work in the pumping work is same as in Carnot cycle. But the process 2 to 3 is the isobaric heat rejection in the condenser in simple Rankine cycle, whereas it was isothermal heat rejection in Carnot cycle. Similarly, process 4 to 1 is isobaric heat addition in the boiler, which was isothermal in case of Carnot cycle. Here it is isobaric heat addition in simple Rankine cycle. Again, the efficiency is turbine work minus pump work by heat supplied as such, and turbine work is H1 minus H2. The condition of the steam entering the turbine may be superheated as shown in this diagram, or it can be one here wherein it can be dry saturated, which is entering the turbine. And 1 to 2 is as usual, it is isentropic expansion of the steam in the turbine. 2 to 3 is isobaric heat rejection in the condenser. 3 to 4 is isentropic pump work, and 4 to 1 is isobaric heat addition in the boiler. This slide shows the comparison of Carnot cycle and Rankine cycle in terms of temperature entropy diagram. So as such, the steam entering the turbine is dry saturated in both the cases, Carnot as well as Rankine cycle. In the Rankine cycle, we can have the superheated steam entry because it is isobaric heat addition, but it is not possible in case of Carnot cycle since it is isothermal, that means temperature should remain constant. Again, the one more difference we can see is the condition of the steam leaving the condenser is again the wet steam in case of Carnot cycle, whereas in a Rankine cycle it is liquid, saturated liquid. And main drawback of this Carnot cycle is it is very difficult to pump the wet steam to the boiler. But whereas it is easy to pump the water or saturated water to the boiler pressure. This slide gives the effect of increasing the boiler pressure and reducing the condenser pressure in a simple Rankine cycle. Increasing the boiler pressure increases the net work of the cycle. We can see the shaded portion is the increasing the work. Initially it was 1 here, that is steam which is entering the turbine. Now with the increase in pressure, the saturation temperature increases. Now it has come to 1 dash. So this increases the total work supplied or total work done in the cycle. And one more thing is the heat rejection, which was initially from the cycle 2 to 3 is reduced to 2 dash to 3 in the condenser, thereby increasing the efficiency of the cycle. And here By reducing the condenser pressure, again we can see the net rise in the work of the cycle from 2, 2 dash, 3 dash, 4 dash, 4, 3, 2. This, the shaded area shows the increase in the work of a cycle. Also, we can observe here, initially with the condenser pressure, it was, the steam was expanding from 1 to 2. So H1 minus H2, it was the Rankine's work developed in the turbine. Whereas with the reducing this condenser pressure, it has increased from H1 to H2 dash. So there is increase in the work output of the turbine. So hence in both the cases, we can see there will be the net increase in the efficiency of the cycle. Thank you.